Good afternoon, fellow OACETT members and guests. We welcome you to our first technical showcase collaboration between Seneca College and OACETT Toronto Central Chapter. My name is Karen Craigs, and I'm a professor at Seneca College in the School of Electronics and Mechanical Engineering Technology, also known as SEMET. We are very excited to share with you today two TPJ 653 presentations and demonstrations from our first cohort of graduating electromechanical students. Before we get started, Seneca would first like to acknowledge the land on which its buildings are housed and where students, faculty, support staff, and members of the public gather. This land is the traditional territory of the Mississaugas of the Credit First Nation. We are guests on this space, and it is our shared obligation to respect, honor, and sustain the land. During our virtual meeting today, we will hear presentations from each student team, with each followed by a 5-minute question and answer period. There will be time at the end of the hour to answer general questions and talk about the program too, if members would like to know more. For our members of the audience, should you have any questions for our presenters today, please type it in the chat as we'll be monitoring that on the go. Or you may raise your hand during the Q&A sessions and we will invite you to unmute to ask your question. So without further ado, it is my pleasure to introduce to you our 3 students today, Matin Zalpour, Kian Hassan-Tehrani, and John Ho. This semester marks our first time running the TPJ 653 Capstone project course, which is a culminating projects course for students in the Electromechanical Engineering Technology Automation, or EMA program. Our presenters have all just completed their program and will be joining the graduating class of 2022. As a special side note, they also recently competed at the Skills Ontario competition in the mechatronics category, which is a provincial competition that takes place every spring. As you can imagine, we are very proud of our students and hope you enjoy their technical presentations today. So Matin will present his project first, entitled Linear Position Control, and Kian and John will present afterward with their automatic valet parking system.
Good afternoon, everyone. Thanks for joining us today and for having us. My name is Matin Zalpour. I will be the first to present. And my project is the linear position control. So here's the project description. This project was created to ease repetitive tasks that require precise positioning in cutting applications such as bandsaws or miter saws. This system can position in metric or imperial from 0 to 254 millimeters in 1 millimeter increments, or 0 to 10 inches in 1/16 increments. The user interface will be with Node-RED dashboard, and we can position the system from there. This project will eliminate the tedious task of manually measuring and setting cut length stops by automating the process and improving accuracy and repeatability. So here are some functional features of our Node-RED dashboard. This will act as the human-machine interface. We have a couple switches on the top of the screen. We have jogging switches for manually jogging the system towards the right or towards the left. We have a go home functionality, which will move the machine to the 0 position to acquire the 0 of the system. We also have an override speed switch, which will, so normally the machine is set to move in slow speeds. By overriding the speed, we can achieve faster positioning. We also have 2 sliders in the middle. One is for metric positioning and the one beneath is for imperial. We can quickly adjust the position using the sliders here, and we can fine tune the final position with the up and down arrows. Underneath that, we have 3 readouts. One is for the accumulated steps. So that is the signals going to the stepper motor. We have the current position readout in inches and also in millimeters. And the enable switch on the top left is for allowing the machine to go to the position once it is selected with the slider. So here's the PCB circuit board design I created for this project. We have a couple pinouts here on the device. On the left side, we have a pulse out terminal, which is sent to the PLC high-speed counter to find the position of the carriage. We have 2 of those because one is going to the stepper motor driver and the other one is going to the PLC input. We have a pulse enable and low speed enable. The pulse enable allows the positioning to start. The low speed enable activates the low speed because there is 2 speeds in the system, high and low speed. We also have some header connections at the bottom to test signals for troubleshooting. At the top, we have a potentiometer, which is a voltage adjustment for the integrated circuits. So this should be set to 20 volts. On the right side, we have the LED power indicator. This shows that the board is powered and everything is working as it should. On the bottom, we have 2 more potentiometers. On the left side, the potentiometer on the left side is used for adjusting our low speed. So once that is set, we can use the potentiometer on the right side to adjust our high speed. There's 2 speeds because when the system initially starts to move, it is in low speed. And once it is not at the destination, the high speed is triggered. And right before the position is about to be reached, the low speed is set to slow down the positioning before reaching our destination. We also have 3 external header pins above the high-speed adjustments. These are used to move the potentiometer to somewhere we can easily reach. So in this case, the operator's panel. So we can adjust the high speed from the operator's panel. And on the right side, we have some external power supplies. We have a 32 volts, 20 volt, and 15 volt external power. Here is the system block diagram. So we have Node-RED communicating to RSLogix 500, which is the programming platform for the MicroLogix 1100 PLC. And they send all the information to the PLC. We also have the circuit board, which is controlling the stepper motor driver, which is sending the pulses to the driver. And it is also talking back to the PLC. And we also have the operator's panel, which is also talking to the PLC, sending information from the push buttons and the potentiometer. So here's the functional features of the operators panel, this one here. So we have two push buttons, numbered 4 and 5. On the left side, it is the push button to jog towards the left. And on the right side, number 5 is used to jog towards the right side. In the middle, we have a potentiometer, which is used to control the high speed, numbered 7. And underneath, we have, the 3 LEDs here, labeled 1, 2, and 3, are just LEDs. And number 2 is used. Number 2 turns on when we're jogging towards the left, and number 3 turns on when we're jogging towards the right. And in the middle of those, we have amber LED, which shows when the PLC is connected to the system. Right now, it is off. So I prepared a little assembly movie here of how everything goes together. So this is the ball screw end supports, which hold the ball screw in place. And these brackets are machined out of steel, which I will talk about later in the slide. This is connected to, this bracket here is connected to the linear bearing nut, and it moves with the linear bearing. This is the limit switch bracket. And this is the motor bracket, which also is machined out of steel to improve heat dissipation in the motor. Once everything's assembled, we can add the pulleys and tension the belt. This is the operator's panel. And assembly is complete. So now I will be demonstrating how this system works. So to start, we need to detent the emergency stop. And the amber LED is turned on, indicating that the PLC is connected. And also the motor is energized, so it is not free to move anymore. So I will share the Node-RED dashboard. This is the Node-RED dashboard, which we will be using to control the system. So on initial startup, the machine doesn't know where it is. So we need to home it to get it 0. So we can do that in two ways, by holding the 2 jog switches simultaneously, or we can use the Node-RED built-in function to home the system. I will switch the go home switch, and once it is on for 3 seconds, it will start moving to the home position. Once the limit switch is triggered, the machine will know it is at the home position, and it will 0 all the readouts on the bottom. So now that we are at the home position, we can position to our desired length. by moving the sliders. So I can fine adjust them with the arrows here. And once I am ready, I can hit the enable switch. So the machine is now at 110 millimeters, and we can use these. We can use this readout to see the position. Once we're at our position, we can also move to any desired position from the current. So if I want to move in inches, I can do so. I will select 2¼ inches. So once I hit enable, it will go to 2¼ inches. So now we are at 2¼ We can also jog the machine by using the push buttons here. So it is set in low speed initially when we're jogging. We can also override this by switching this here, the override speed. So now it will jog in higher speeds. While jogging, the position is not lost, and we can retain the position, and we can see where we currently are at with the readouts at the bottom. So currently we're at 70.5 millimeters. So if I want to move it to 80, I can do so from the current position. So now we are at 82 millimeters. And the accumulated steps is the amount of pulses that are being sent to the stepper motor to get to that position. And now I will demonstrate the maximum positions by going to the maximum position here. So I will move to 254 millimeters. So now that we are at our maximum position, if I try to move further, it will alarm out. So the only way to revert this is by jogging the opposite direction. So now we are okay to travel to other positions. I can also, it moved back to, I can also demonstrate the high-speed function here with adjusting this potentiometer. So I will go back to 93 millimeters. If I adjust this, it will slow down. We are back at 93 millimeters. And I will go back to the presentation slide to talk about a couple more things. So I prepared a cutting application demo video to show how this would be used in the industry. So this was a cutting application, and the system went to the position it was selected to, and the material was brought up against the stopper, and the cutting procedure can continue. So here are some functional features of the safety devices that are in the system. We have our proximity switch, which was used to detect the maximum travel, which I demonstrated. The limit switch is used for homing, and also for stopping any travel in the right direction that exceeds our maximum. We have an external emergency stop, which will cut power. I can demonstrate. So now all power to the motor is cut off and the system can be moved manually. After pressing the emergency stop, it is recommended to rehome the system, and because the system was turned off, it needs to be rehomed. We also have a short circuit protection on the main side, which is a 1.5 amp use. So here is a progress flow diagram I created to show my progress while I was designing the PCB. So the progress is noted in blue. So when I face the problem, it is noted in red, and the solution is showed in green. So the first step was to create a 0 to 10 kilohertz pulse generator. Next was to transfer these pulses generated to the motor driver and the PLC. After doing this, I encountered a problem, and the pulses sent to the driver and pulses coming from the PCB do not match. So when the transistors were switching, I was able to test with my oscilloscope that the pulses coming out were not matching the pulses being sent. So this would result in over travel. The solution to this was to use an AND gate IC integrated chip instead of transistors for the switching. So another problem was the PLC was not receiving all the pulses sent by the circuit, the PCB. This was because the chip I was using was rated for 5 volts, and the PLC doesn't detect the signals coming from that chip because the voltage level was too low. So I needed to switch to a CMOS chip, which allows higher voltage outputs, and this solved that issue. So next was the voltage regulator was overheating. A simple solution to this was to switch to a BX7815 regulator, which is capable of handling up to 500 watts of power. Next was to implement the low and high speed functions. And once everything was working, I was designing the PCB. Here's the circuit wiring diagram. Over here, we have our pulse generator, which is the 0 to 10 kilohertz using the LM555 integrated chip. Here we have our low speed function, and it is a MOSFET, which puts the 2 resistors in parallel when activated, which reduces the pulses being sent to the driver. So in turn, reducing our speed. Next here is our switching. It is done by the AND gate. And on the bottom is our power supplies. And on the right is our breakout connections. So here are some components I needed to build for this project. And I used Siemens NX to help me manufacture them easier. So this is the support for the bearing blocks. It attaches the bearing blocks to the frame, and it is made out of steel. This component is 3D printed, just for time's sake. And it is used to connect the carriage to the ball screw nut. There's another component that was made out of steel, and it was bent to the desired angle to connect the ball screw nut and the linear carriage together. This is the motor bracket, which is used for tensioning the belt, and also it is made out of steel to help heat dissipation in the motor. Here are some couple 3D printed parts. The one on the left, top left, is the limit switch bracket. The one on the top right is the proximity switch bracket. The one on the bottom left is used to keep the cables inside the aluminum extrusion, so it just snaps into the aluminum profile. And on the top, we have the measurement readout, which is also 3D printed. So here are some project photos, some closer photos of the project. And here's some technical information. So we have a 2-to-1 gear ratio. The motor is driving a 48 teeth pulley, which is driving a 24 teeth pulley, and it gives us higher speeds. And the ball screw has a 5mm pitch, so we can achieve more accurate positioning. The motor, the way the stepper motor works is it receives pulses, and to turn 1 revolution for the motor, we need to send it 1600 pulses. And for every rotation, the movement of the carriage moves 10 millimeters. Here's the linear travel per step sent to the motor. It is fairly accurate, and plus or minus 5% from the stepper motor driver. And the maximum speed we can achieve is 1.8 inches per second. The software is used are RS Logic 500, which is used to communicate to the PLC. Boot P DHCP tool, which is used to set an IP address to the PLC, so we can use Node-RED to talk. And Node-RED for our visual interface. That is all. Thank you. And if anybody has any questions, feel free to ask.
So we are inviting questions from the audience. If you wish to ask Matin some raise hand. Ashley, do you have a question?
I do. So I know you demonstrate, oh, first of all, thank you very much. That was a great project, great presentation. I know you demonstrated.
Sorry, I think we're just having a speaker issue here.
Oh,
1 second.
okay.
Sorry about that. Should I turn up the volume on this?
Can you hear me now? Sorry. I have some construction happening here in the house. I know you demonstrate. I said thank you very much. That was a great presentation. Really appreciate it. I know you demonstrated one use of this equipment in the industry. What other uses can this be used for?
So we can use this for anything that needs a precise positioning. So yeah.
Like for cutting, for example, materials?
Yeah, that's the main use I find for cutting applications.
Okay, okay, thank you. Thank you.
Thank you.
We have a comment in the chat from Nitesh. Great job. I don't see any other questions or hands up. There will be time at the end of the hour for follow-up questions if you wish. So let's get set up for our second group, Kian and John.
Good afternoon, OACETT members. My name is Hassan-Tehrani.
And my name is John Ho.
And this is the automatic valet parking system. Being stuck in traffic is not fun, especially when you have a meeting to get to or an interview for a job. Now you're stuck in traffic. This can happen to the best of us. And most of the time, we can't do much to favor us. We found one solution to one cause of traffic. Cars that park on the right-hand side of the road at pay meters cause a lot of traffic in busy cities. This makes it difficult for cars to drive in both lanes.
So we have been working on an engineering concept design prototype, aimed to provide a workable solution for the parking issue we've mentioned. We wanted to assist drivers to make parking more convenient and simpler. Here we have a clear view of our project. We have the PLC and power supply on the right, and the automatic parking system on the left. The overall concept of our project is that a car would come in and stop at a specific parking location. It can be either on the side of a crowded road in downtown or near the entrance of a mall. Then the driver would just follow the instruction on the meter to pay, just as how you normally do it to park on the road. And an automatic system would then take the car down to an underground parking garage and will be stored there for the whole duration. There's a total of 2 available parking spots beneath. When driver needs to retrieve their car, the jack lift will then lift the car platform back to the road, and the car is now ready for pickup. When we were designing the system, we have included a safety feature to ensure the parked vehicle is within the boundary of the moving platform. There are 2 IO sensors located at both ends of the platform, and also a pressure sensor on top of it to detect the position of the car. A buzzer will alert the drivers if they are not positioned correctly. Also, to find a free parking spot, the driver can also check which spot is available using the Blink app on their phone in advance. Here we have a system block diagram. We use a electronic PLC to program the sequence of the parking procedure and to control all the movement of our system. For inputs, we have the limit switch and proximity sensor, help to tell the PLC what is the current position of all the moving components. For example, whether the jack lift is in its upper or lower position. For output, we use DC motors to move the cover, the jack lift, and the underground platform. On the other hand, the particle photon, which is an IoT microcontroller, oversees the safety feature of the system and is connected to the Blink cloud to communicate with driver's phone.
For a project hardware overview, we have the inputs in the blue, the MCU in red, the outputs in green, and the other hardware in purple. To go in more detail about our project hardware, we start with the inputs. We have 2 limit switches to stop the y-axis from moving up and down. The reason we chose limit switches was because of the physical contact it has rather than a proximity sensor. Next, we have a push button and a toggle switch. The push button is used as an e-stop to stop the whole system as is, and the toggle switch is to switch in between automatic mode and manual mode. Manual mode is used by an authorized personnel to do any service or maintenance that is needed on the system. Next, we have 3 proximity sensors on this project. One is an inductive sensor for our upper limit, and 2 magnetic reed switches for our lower limit. Next, we have 2 infrared sensors working alongside 2 pressure sensors and an active buzzer to indicate the driver if they're not parked properly on the platform. Next, we go on to our outputs. We have a green LED indicating that the platform is ready to be used and is at home position. And we have a yellow LED indicating that the platform is either moving or is not in home position. We have 3 high torque DC motors, 2 of them being 200 RPM DC motors for our platform, and 1 being a 50 RPM DC motor for our y-axis to move up and down. Next, we have an HMI display, which is on our PLC. It's an LCD screen, which has a size of 2 lines, 16 characters long, with 16 keys on the keypad. Next, we have our MCU. Our MCU is a Unitronics PLC. The model number is JZ20-T40. It has 18 digital inputs and 20 digital outputs. Out of the 18 digital inputs, we are using 10 of them, and out of the 20 digital outputs, we are using 11. And the input type is either PNP or NPN. We also have a particle photon, which is an IoT development hardware tool. Equipped with a Wi-Fi chip, it has its own online cloud application. It's also easy to integrate with other applications such as Microsoft Azure's IoT Hub. Our other hardware includes dual H-bridge drives to control our motors, a linear actuator for a cover so cars can drive over once cars are parked underground, and a computer power supply. The motor design and functionality works by a motor turning a threaded rod to lift the platform. A magnet is placed near our reed switch so it can detect if the platform is closed. As the platform rises, you can see that our inductive sensor is detected by a metallic tab. To go in further detail of our jack functionality, the jack works by a threaded rod turning a threaded bar to lift the platform. The mechanism of the mechanical design of the jack is similar to a scissor jack. As the threaded bars move towards each other, the jack rises. Our computer power supply is used to connect our H-bridge, motors, linear actuator, IoT, and PCB. We took apart the computer power supply to access the 3.3 volts, 5 volts, and 12 volts. This gave us the ability to use the appropriate voltages for our outputs. To be able to use our various voltages with our PLC, we had to use relays to switch from a 24-volt output to the various voltages. For our CAD designs, all parts were designed on Siemens NX to later then be 3D printed. On the screen right now, you can see our motor mount for our timing belt. Small details that make a big difference on the mechanical stress of our 3D printer is the edge blends that we do on every corner so that there is no hard edges. To the next CAD design that we have is our pulley mount on the other side of the motor mount. This is designed to the perfect height of the motor mount, so there's no jumping on our timing belt. The next final CAD design that we have is a cover to hide the linear actuator, and there's also a circular opening so we can place the buzzer within it.
Our project has also incorporated our own PCB design. It is a custom-made shield specifically for the particle photon. As you can see, it has a built-in LED light to indicate the status of the pressure sensor, pull-down resistors, and also the terminal block connector for easy and clean wiring for all the inputs and outputs. Now we'll talk about the software and program of this project. For the PLC, we use the Unitronic United Ladder software to program the sequence for the parking system, and for the display and button on the HMI as well. It uses ladder logic programming languages. For the particle photon, the program is written in C using the particle web IDE. The program is mainly for sending information to the cloud. Finally, for the mobile application, we did it in the Blink IoT app, which is available in both iOS and Android.
Now it's time for our project demonstration.
So for initial setup, the system will need to go to home first. To do that, we'll press home on the HMI. And once it's at home, the green LED light will turn on to indicate that. Now the platform is ready to use. So first, when a car wants to come in and park, it will drive and stop at the platform. And when the pressure sensor detects the presence of a car, the safety feature will be activated. And the two IO sensor will sense whether make sure it's within the boundary of the moving platform. If not, the buzzer is going to be turned on. Now the driver can get out of the car and follow the instruction of the meters. It will first ask the driver whether they want to park or pick up their vehicle. So all you need to do is just press park. And the platform will start moving down to the underground garage. And if the other spot is available, it will then move up the other platform. Now another car can come in and park to it. So if both parking slots are used, the drivable coupler will then come in, allow incoming traffic to move. Now, to pick up your vehicle, all you need to do is press pick up on the HMI and choose which parking space you use. Now we'll talk about the IoT application. Using that Blink apps, we have make an IoT application to indicate that which parking space is available. So if the spot is used, the green LED will turn off. Green LED will turn off to indicate that the space is used. We also have a menu mode for the system. So all you need to do is toggle the menu mode and then follow the instruction on the HMI to merge each individual moving components. This is especially useful for maintenance.
Now moving on to our product.
So here are some of the advantages of our automatic parking system. First, it's easily accessible for drivers. It means you don't have to worry about doing parallel parking or backing into a really tight spot. Also, it uses space more efficiently. As we've mentioned before, storing vehicle underground instead of on the side of the road can reduce blockage of incoming traffic. As a result, minimize congestion on small city road, especially in the downtown area. It is also secure and safe because the vehicle will be parked underground. It reduces the risk of someone breaking into your car or even scratching it. Finally, it's a fully automatic system that allows your car to be parked without any human assistance. This can prevent many accidents that normally can happen in the parking lot as well. We think our automatic valet parking system is a new futuristic way for parking, as the world and the industry are moving toward automation and robotization. It can be an efficient solution to many of the parking limitations we have talked about. We think it can also provide a platform for collecting driver's data and parking behavior for city planning and vehicle data analysis.
Moving on to our challenges and lessons learned. During this project, we actually had a lot of challenges, but we also learned a lot from those challenges. To go in more detail about our challenges, our first one is with our PLC. Prior to using the Unitronics PLC, me and John didn't know much about declaring inputs as NPN or PNP. So prior to doing this, we had a floating voltage in our inputs and we couldn't figure out what the issue was, and none of our inputs were working properly. Through further investigation in the manual of the PLC, we could see in bold text, it says that N/P pins must be connected. After doing some more research, we found out that we needed to declare the inputs as the PNP source. And once we did that, all the inputs were working perfectly fine. Another main challenge that we had was the mechanism of the jack. The mechanism of the jack was challenging to us because we're more used to electrical engineering rather than mechanical engineering. So once we purchased the jack, we didn't think that the threaded rod would move inwards as the jack moved upwards. So once we got it in our hands and actually tested it, this was an issue because we needed the motor to be mounted onto the platform. So we took the jack apart and we threaded out one of the threaded bars so that there's only one threaded bar pulling the jack upwards. And we attached a motor coupling on the other side of the threaded rod so that it doesn't move inwards.
Finally, we'll talk about the future changes we'd like to make to our project. First, we would like to take advantage of its IoT capability to help and improve businesses by connecting it to the Microsoft Azure IoT Hub. It will allow companies to collect and send data of the parking system to the cloud for further data analysis and also open up more opportunity for other Microsoft services. For the mobile application, so right now you can only check which parking spot is free on the phone, but we would like to add way more user features, such as remote control and time setting for vehicle pickup. The last thing we would like to do is to improve the safety and security of the parking system. That can include requiring password for vehicle pickup or some kind of safety feature to prevent driver from getting into the underground garage.
Thank you very much, OACETT. That was our presentation and we are open to questions.
Some comments in the chat. Good job.
Thank you.
Any questions from the So one question is, what happens when it gets full underground?
Cover, if the parking lot underground is full, the cover will come, so it's a drivable cover, so cars can drive, so traffic is not stopped because of that.
Another question is, how do you see this application being scaled? Or
To more parking lots, right? To expand this parking lot more, we've been thinking of adding like more platforms underground by adding more sensors to detect which platform is under the opening.
question from the chat. In terms of city infrastructure, operation, and safety related issues, for example, weather and flooding, have you had any studies or suggestions on that?
To be honest, no, not as right now. It's an engineering concept, but we would for sure look into that if we were going to implement this into the real world, for sure.
All right, so let's come back here. Thank you so much for joining us today. And we are opening, so in our final 5 minutes of the session today, just thank you very much for being here. We're super excited to be in collaboration with OACETT Toronto Central Chapter. So thank you, Akriti and Catherine. Hopefully we'll gain some new ideas for future technical showcases. And thank you to our presenters, John and Kian and Matin. Thank you to Summit for helping us organize, especially to Fabio Costa and OACETT in general. All right, so we'll call that a wrap. And thank you so much for joining us today. And we hope to see you in future.
Catherine?